started? So I just sent out an announcement on my way over here that don't forget there's an exam retake survey for extra credit. If you, after it's completed, it's submitted to the education group I'm working on. They'll send me a list of names after it closes. It closes on, I think, Monday, the 18th. And so once they get all those names, there's about 54 out of the 82 of you, and we'd like to increase that response rate's great, but the more we have, the tighter our confidence intervals are. So trying to get as many samples as possible. So if you're interested, please, the instructions, again, I just sent them out on my way over here. And I'll send another reminder out on Sunday on Canvas. So that, just as a reminder that that's out there. Otherwise, there's an interactive Canvas activity, L, which is kind of our last like new content Canvas activity about the current stuff that we've been talking about. And then there's final exam review stuff. And so this ICAM is one of these ones where you can take over and over and over again, and it just samples from all the previous Canvas activities, maybe with a couple of slightly newer questions tossed in. There is if you want to go back through and practice the material from before the midterm, then that old Canvas activity is available as a practice assignment, no credit awarded. And then once this one disappears, it will turn into a practice assignment. So this one's due during lecture in, which is the final exam review, which is the Tuesday of the last day of classes. And so once we have that review, then it will turn into this one, and then you'll have those practice assignments available through the end of the semester. And then other final exam resources are on Canvas under the final exam module. There's example exams from the past 2 or 3 semesters. There's some extra problems and solutions that are out of the book, and a couple other similar things. And so plenty of that available. And if any questions come up as you're starting to review towards the end of the semester, feel free to let me know. Otherwise, homework J2 is available. It's an arena-based homework. We're going to look at that Bucky inventory management problem that you built 2 models of, one with the old blocks and one with the new blocks. So we give you the old blocks model and you can modify it, or if you have the new blocks model that you'd rather modify if you feel more comfortable with those, you can pull that out of your lab submission and use that instead. You can do this all by hand by running these things, or if you'd like, it might even be faster if you make use of that process analyzer. So take a look at that process analyzer video that I made for Lab 10, and that shows you how to automate the process of running experiments. Because what we're going to do is basically say, well, what's the best little s and big S for certain situations here? And rather than you manually running a bunch of those yourself and then trying to find those confidence intervals, that it's a lot easier just to say, all right, have process analyzer go and run 4 or 5 scenarios, and then have it automatically generate a nice box and whiskers chart that ranks them all for me, so I can say that this scenario is best. So, so that's good practice for that. And then otherwise, today or this week's lab is the last lab. I had forgotten on Tuesday that I had given you 2 weeks to do it, so that's why I put out that reminder. Since it sort of has this bonus lab bolted onto it here, then it's not due this Sunday, it's due the next Sunday. So you've got all that time to either just do the first part for 30 points, or if you want to do both parts, then you can get up to 50 points, but it's still graded out of 30. So it's almost like a replacement lab is baked in there. So part 1 introduces you to sequences. So especially those of you doing like the arena competition where you've got things moving from port to port, or if you've just got a lot of other things where you're imagining entities that are being routed from one area to another, but some entities might take one path, but another entity might take another path, and maybe those paths even change during the simulation. Sequences are much, much easier because you don't have to hardwire those sequences. You can just set up the stations, and then in a sequence you can say, on this schedule you visit A, B, C, D, but on this other schedule you visit A, C, D, B, and then maybe A, B, C again, and we can switch between those schedules even dynamically. So, so that's a nice tool to have there. And then part 2, the bonus part, it describes batching, which kind of reminds us back to the muffin simulation in Lab 2, and things that assist us with batching, like signals and holding. And so if you've got a sim where you would really like the sim to wait for another condition to be true in another part of your sim, then you can put a hold in one area and it will wait until a signal is sent from another area. So that's another very powerful tool. So that's kind of the intent of this lab, is to introduce those features there and then give you more sort of reason to play with the process analyzer, or maybe even Hoc Test, which can also be very helpful for your final project. So, so next week there's no formal lab, but again, this is due not this Sunday, but the next Sunday. The week after that, there's no formal lab. So you can use both of those as open labs to get final project modeling help. And then the week after that is, I think, when you actually present in your lab section. So it's giving you an idea of the timeline going forward. So and then presentations. Presentations, about 10 minutes of presentation, 3-minute Q&A, and then your report will be due that week as well. And there's the desired 4-page format is online on campus. So, kind of lightning announcements, or any questions about that? Just a reminder that extra credit survey is online. That's 4 points in the homework category. It closes on the 18th. I think the night of the 18th, Monday the 18th. And if you need the link to that, I just sent it out. You can also find it in the announcements, and I'll send out another reminder announcement on Canvas on Sunday. All right, so let's start with a little attendance exercise. And so you can chat with your neighbors about this, but take 30 seconds to think about this. If I gave you a point estimate, you could say that point estimate is equivalent to a confidence interval. You have to pick the right confidence level. So what is that point estimate? So is a point estimate equal to a 0% confidence interval, a 95% confidence interval, a 100% confidence interval, or is this all a lie and your escape option here is it's just, it's different. It's not a confidence interval at all. So, so again, feel free to chat with your neighbors and then pick one of these. So what is a point estimate? What confidence level corresponds to you giving a point estimate? All right, so how many people think that a point estimate, how many people chose option D? How many people chose option C? All right, so a couple people chose option C, sort of implying that I guess the rationale there is that if I give you a point estimate, I'm 100% confident. How many people chose option B? A couple people chose that. The rationale might be that 95% confidence interval is our sort of standard confidence interval. How many people chose option A? There's a few more chose option A. Rationale here, I give you a point estimate, I have no confidence in my estimate. That was the option I was looking for, is option A. And so the idea here is that as you make your confidence intervals, as you make your confidence level larger, your confidence interval also has to get larger, because the only way you can have 100% confidence that your interval includes the mean you're trying to estimate is if it includes everything. So a 0% confidence interval is when the confidence interval collapses to a point. So if you give somebody a point estimate, what you're actually telling them is there is actually 0% chance that this is the real mean. This is just a number I calculated from data. I'm not telling you how much data. I'm not telling you about the variance in the data. I'm just telling you that I used a calculator. And so a point estimate is a 0% confidence interval. Now, related to that, so let's say I gave you these 3 confidence intervals. So here's part 2 of this, or question 2 of this attendance exercise here. So assuming that I had similar standard deviation in the real process, and I calculated these 3 different confidence intervals, which of these 3 confidence intervals corresponds to the one where I use the largest amount of data, the largest number of samples? So feel free to chat with your neighbor, and then think about that. Which confidence interval here corresponds to the most number of data? And basically I have a medium-sized confidence interval, a small confidence interval, and a large confidence interval. Medium, small, large. All right, so I'll go from the bottom to the top again. How many people say that the largest number of samples is the largest confidence interval? Option C. How many people say the largest number of samples is the smallest confidence interval? Option B. How many people say the largest number of samples is the moderate one? Right? I think all the hands I saw were for option B, and that's what I was looking for. As you increase the number of samples, your confidence intervals collapse. I noticed now the temperature's gotten a little cooler. Last night, my car's tire pressure light came on, and I happen to have a radio that shows me the tire pressure in each of the tires. And I was thinking like, oh, that's a point estimate. How can I have any confidence in this? And then I, put air in my tires, and then I looked at it, and it showed me the old values until I drove around a little bit, and then gradually one tire turned on or updated, and the other tire updated, the other tire updated, the other tire updated. And the reason it took so long for those point estimates to update, well, there's lots of reasons, but let's just pretend this is the only reason, is that effectively it didn't want to take one value at that tire pressure sensor. It took several values and averaged them out. And so in order for it to give me, the end user, a point estimate, and for the designers to be confident in it, it had to get a lot of data. So when we give point estimates to the rest of the world, we have to be very confident. We have to make sure that our confidence intervals are very tight, and that usually means we have to find a way to gather a lot of data or reduce our variance, and that'll be some of what we'll talk about today. So, and then I mentioned that we'd like our response rate on the survey to go up. We're trying to bring that confidence interval down. We like more people to vote. We're trying to bring the confidence intervals down. So confidence intervals, you want them to collapse around to a point, but not because you changed the confidence level. For the same confidence level, you want to gather more data so you can have them collapse around a point. All right. So, are any questions about that? Does this seem pretty good that the point estimate is a 0% confidence interval, and for, say, a 95% confidence interval, the smallest interval has the most data. All right. So, last time we started talking about for the one sample case, how a confidence interval is just a graphical interpretation to a one sample t-test. And so the idea here is that if I were to do a t-test, and I have to assume normally distributed data, and that I'm only making an inference on the mean of that data, then if I am under the null hypothesis, so if the null hypothesis is true, then sometimes I'm going to get samples, x bar, that are far from the mean, the actual mean, theta. But it's not going to happen that often. So if I get samples that are far, and this is all standardized, so we create a threshold here, then we reject the hypothesis, because it shouldn't happen that often. And so this condition here we said that if you just do a little algebra, corresponds to this condition here. So finding out that your data are very far from your null hypothesis could be flipped around to saying that you calculated a confidence interval and the null hypothesis is outside of the interval. These are equivalent conditions. But going the other way around, if I can't make a decision because my data are too close to the mean, then that's equivalent to saying that my null hypothesis is inside the confidence interval. So in that case, I can't really say that I can reject my null or not, but I just know that I definitely don't have any evidence to reject it. I can't necessarily accept it, but I at least know that it's not part of the group that I definitely can reject. And so that's the inside and the outside of the confidence interval. And so that is just, whenever you see a confidence interval, you can do a t-test immediately. So the one sample rule is if your confidence interval does not include the mean, you reject that hypothetical mean. And so our confidence intervals down here, mathematically speaking, is that under the null, if the null is true, the probability that the null will be inside the confidence interval is whatever the confidence level is. So that's what we mean by 95% confidence interval. We're saying if we're in a world where the null is true, this interval we're showing you will capture it 95% of the time. And I showed you a bunch of graphical versions of that, where I just drew 100 confidence intervals under different conditions, and these are all 95% confidence intervals, and so 95% of them happen to capture the real mean, which is this dashed horizontal line here, and there's only a small number of them, roughly 5%, that do not include that mean. And so what I'm showing you here is I've got a small number of samples, 20 samples, 200 samples, and 2,000 samples. And you can see that I always have 95% of them capturing the mean, but the ones that do capture the mean are much, much narrower. And so we have much higher sensitivity. We are effectively rejecting more and more hypotheses as we get more and more data. Now, on the flip side of that is if I've got a system that somehow increases in variance and I use the same sampling strategy, then my 95% confidence intervals, these are all 95% confidence intervals, but here's low variance, here's moderate variance, and here's high variance. And as I increase my variance, it is always the case that 95% of my confidence intervals capture the mean. But as the variance goes up, the blue confidence intervals increase, and so I lose sensitivity. It becomes harder for me to discriminate. There are more and more hypotheses that I do not reject because those blue bars get much larger. So that's the intuition I want you to get. Because what we'll see here is that although we want to make sure we can do t-tests and things like that, when professionals show data to each other, then they usually show these confidence intervals. And so you need to be able to look at an interval and be able to make an interpretation from that. And so here's an example. So this is data I took from a real paper from a colleague. And so the context of these data don't really matter, but there is some independent variable that they've plotted here and some dependent variable that they've plotted there. Here are the real data here. They happen to log transform both just to make sure that it fits on a line. And then they did a linear regression. So you've done linear regressions before, just a standard linear regression, and here's the slope and the intercept. And I've highlighted the slope, and it says 0.7845. So that is the slope of this line that they fit through there. But even our point estimates of this relationship have confidence intervals. And so every linear regression is going to come out with a confidence interval on all of the regression coefficients. And so in their paper, they reported down here that the best fit was a scaling relationship to the 0.78 power. That's that 0.78. And then in parentheses, they say 95% confidence interval from 0.671 to 0.898. So that's what I've depicted up here, 0.671 to 0.898. So they're already telling me that this is our point estimate, but in reality, it could be really anything in this interval. But then they go farther than that. They take this graphical interpretation, and this is the standard way you would present this. They even do a little bit extra that I say they don't even have to do. But they say this scaling exponent is statistically less than 1. Well, what do they mean, statistically less than 1? What they mean is that this confidence interval does not include 1. It's entirely to the left of 1.0. So they have rejected the hypothesis of 1.0. In other words, it would be interesting if this was a 1.0 line, but the fact that it is less than a 1.0 line rejects the null hypothesis. So it turns out in this paper, people thought the relationship between these two, this independent and this dependent variable, would have had a 1.0 relationship. And they said, no, we took our data, and 1.0 is outside the confidence interval. We reject that. Yeah?
Just to clarify, when you say power there, you mean the same thing as 1 minus beta?
No, I'm sorry. So that's it. So because this is they're showing a power law relationship, like, x to the alpha. And so they took a log law so that the slope of the regression line is actually the exponent in the power law relationship. So that's just a data transformation. And I apologize for that ambiguity. That's I'm glad you mentioned that. Yes, this is not statistical power. And then so not only do they say it's statistically less than 1, but they go further and say it is not statistically different from 0.75. So it turns out in the literature, there's kind of two options that people debate. Is this particular relationship a 3/4 option or a 1 option? And they took their data and they said, look, our confidence interval includes the 3/4 option, but it does not include the 1.0 option. Now, statistical power, we don't actually know that 0.75 is the real scaling exponent, but we know we can't exclude it. But we definitely know we can exclude the 1.0. So it pretty much is not going to be the 1.0. So that's why I put the null is the 1.0. The alternative, which we found support for, but we can't totally accept, I put this HA above, H alternatives, this 0.75. And they've gone, and in the parentheses here, so this is the standard way you report stats, is they have DF equals 27, T equals 14.2, P is less than 0.01. That's the one corresponding to the null hypothesis. So the DF is going to be, what is the D? What is this? Why did they report this DF? What is DF? Degrees of freedom, right. So you always report your degrees of freedom with your statistical test. So this is saying we had 27 degrees of freedom, which means they had 28 data points. So I bet if I counted these, I get 28 points. They calculated a T statistic of 14.2, which was well outside of the critical value for this number of degrees of freedom, and so their p-value was less than 0.01, which is far less than 0.05. And that corresponds to the outside the confidence interval. So I would say they didn't even need to include that. But then they also did it for the alternative, and they said, again, same DF because same number of points. This t-value, very small, so it did not reach significance, and the p-value is greater than 0.05, and that corresponds to it being inside the confidence interval. So this is how you report empirical data, and you usually use confidence intervals to make it easier for people to see. You can go even farther than that. Here's another paper that I just dug up from another colleague, and again, the context doesn't matter, but again, I put regression coefficients that they were interested in, and they didn't even give us any statistics. They just gave us confidence intervals, and then they marked the ones that showed a significant difference from 0. So he's got these different response variables here, and then he's got these different coefficients. He put a point estimate outside here, but then he put the confidence interval, and it says 95% confidence interval. So he put a 95% confidence interval here, and then puts the little note that the ones with a star by them do not include 0. And so, again, he doesn't even say I did a t-test or whatever. He's just counting on you, the educated reader, to know that this confidence interval does not include 0, which means this is significantly different than 0, that you can trust that the relationship here is negative, negative, and negative, but up here, even though the point estimate is negative, because the confidence interval includes 0, we actually don't know what the actual regression coefficient is, and we can't really pay much attention to that. But we can pay attention to the negative relationships here. So that's why I want you to get comfortable with looking at confidence intervals, because as you start working with professionals, they'll just start only giving you confidence intervals and assuming you know what the hell that you're looking at. So there are questions about that. Is it clear that we're now moving from point estimates and t-tests into a world of intervals where we ask what's in the interval and what's not? All right. So now you'd say, well, a lot of times I want to compare two things. I don't just want to say, is one thing in the confidence interval or not? So how do I start comparing two things? So I've already learned all this stuff about one sample confidence intervals. Is there a way that I can compare two one sample confidence intervals? And it turns out there's a special case where you could do that. You could take a bunch of data on one response variable and a bunch of data on another response variable and calculate their confidence intervals and then compare them. And if they do not intersect, so if they're mutually exclusive, if they have gaps between them, if they're totally separate, then in that case, you can conclude that if you were to run a two-sample t-test, these two populations would be statistically significantly different. They would be different populations. It would be unlikely that they were drawn from the same distribution. So that you can do that when the confidence intervals do not overlap. But unfortunately, when they overlap, you can't make any conclusion. The p-value of a two-sample t-test might be less than 0.05 or it might be greater than 0.05. We don't know. So this is a kind of a simple shortcut that is often taught, but you have to really reinforce that this shortcut only works for this one case when there is no intersection between the confidence intervals. When there is intersection, you don't know. So as an example here, these are data from two HIV detection methods, so A and B, and these, the response variable here is days until the HIV detection, so the test here is to see is method B quicker than method A. And so initially, these are 95% confidence intervals. And so when you look at these data, these intersect. And so you might say, there's no difference between these two. I can't tell a difference. But it turns out if you put the actual data into a two-sample t-test, you get 0.049. So you actually do get a significant result. So to a 5% significance level, then it is that this detection method is faster than that detection method. But I couldn't tell that just by looking at the confidence intervals. So you have to be careful here. But if there was daylight between the two, if this was down here, then I could have immediately made that conclusion even without the test. Question?
Yeah, so that means that when they do intersect, like you would have to recur to a t-test just to confirm.
If they do intersect, yeah, then I just dump take all these data and all these data into a two-sample t-test, which we'll talk about today, and then I would get a value, and I'd have to interpret that value. But if there's daylight between them, I don't even have to go that far. All right. So that's kind of leads into what we're going to be talking about today is then can we build a new type of confidence interval so that we can import all of our geometric intuition from the one sample case to the two sample case and have it work for sort of both p-values that are greater than 0.05 and less than 0.05. So how do we make this work for both cases? And so we need a sort of a special confidence interval, which will be a confidence interval of the differences, as opposed to two confidence intervals. So that's what we will talk about today. But then just as a reminder of our context, so we've introduced in your simulations these two types of simulations, the transient simulations that correspond to modeling terminating systems. And the big question there is how many replications to run. So if you use the homework G3 model, you use a power analysis, and that can tell you how many replications to run. Or if it's a little simpler, use the model from Lab 9, which is kind of like what we've been talking about lately, where somebody says, I want my confidence intervals to be so small, and then you can use that to figure out how many replications to run. The other type of sim that we've been talking about, so there's the formula for that as a reminder. The other type of sim we've been talking about are these non-terminating systems, which we are interested in steady state simulations, where we now have another problem is how much data to get rid of, and how do we deal with the issue of needing to run a lot of replications, and the fact that every replication we have to spend a lot of computational time just dealing with transients, and so it seems like a lot of wasted time. So how do we manage that? And so we talked about how, well, you just initialize the simulations a little smarter, maybe by using mathematical models. Maybe you create this warm-up period I was just talking about. Or maybe there's actually a way that even though your analysis of the confidence interval says you need more replications, maybe there's a way for you to actually run one replication for much, much, much longer, and then you only have to pay this cost once. And so we talked about there are these simple rules that down here that sort of decide what regime you're in, and once you hit 25 replications, it's better to increase your time as opposed to increasing your replications. And by increasing, if you need 20% more replications, instead you increase your times by 20%. And what's nice about that is you actually decrease the variance in your population, so your confidence intervals will go down. But you also throw away more data, and so, but while not using any more computation time, so your bias goes away as well. So this is a good solution, especially when you have a lot of replications already. And then if you take that to the extreme, you batch everything together where you just run one replication for super long, and you create batches where each batch is so long that the numbers you average on one batch have no predictability for the next batch. So even though I've only run one replication, I can treat it like k independent replications. And this is what's done behind the scenes in Arena. If you tell in the run setup to only run one replication, but you run it for long enough, then if you were to look in your reports or if you were to export that Excel CSV file of the replication data, it will give you confidence intervals. And you say, well, where do these confidence intervals come from? I only ran one replication. Well, what it did was it created sort of fake replications out of your long replication, and it sort of figured out what the best way to chop this stuff up is. And so if it doesn't give you a confidence interval, instead something like insufficient data or correlated data, that just means that if you ran your sim for longer, it might have been able to simulate having independent replications, but for the length of time you chose to run your sim, it couldn't. So the best you can do is just taking one sample at the end of your replication. But if you run them long enough, it'll eventually be able to generate a variance and thus generate a confidence interval only with one replication. And that's the magic of batching, which you can do in these steady state simulations. All right, so any questions about the past stuff? All right, so yeah, this is the last section of this unit of estimating performance. And we've moved from 3 lectures on absolute performance to finally relative performance, where this is kind of our motivation, at least for the first part of this, is how do we build a confidence interval that's like our one sample confidence interval, but allows us to make 2 sample inferences. So instead of saying, is the mean of my response variable equal to a certain constant, then I can say, are these 2 systems equal or different? And so the picture I want you to think of is, what if I had 2 models? I have model of system 1, model of system 2. And these are hypothetical call centers. And so in one call center, then maybe this is our as-is system. We've got callers that come in, and then they get dispatched either to billing or support. And so I've got 7 operators here. These 4 can only do support. These 3 can only do billing. Roughly 60% of my calls go to support and 41 go to billing, but it might be that these billing calls don't take that much time, and so my billing operators have a very low utilization. And so I might be interested in knowing, what if I trained these billing operators to do support and my support operators to do billing? So with that cross-training, I could just get rid of this caller selection. That maybe actually simplifies things for the callers, because they don't have to tell me what they need. And they just go straight through to an operator that's been cross-trained on both jobs. And maybe then I'll actually have less utilization, or I'll have a utilization that'll be more, like these ones might be a little less, and these ones might be a little more. So the average here might be like 50% utilization instead of like 90 and 20. And so then, so the question is, how will that affect my callers? And so I might run a simulation of this model and a simulation of this model, and then I might measure things coming out of that. Like it might be that I measure the caller wait time, for example. So I run our replications of this model, and I see how long did they wait in order to get serviced. And so I've got 1 replications data, 2 second replications data, all the way up through, and the average of all those replications. And then I do the same thing for my other model. So I've got all of the same data here, and maybe I ran even a different number of replications, maybe because I had more variance in one than the other. And so then I've got 2 means, and my question is, by these 2 samples, can I say that these 2 models are different? Can I say that this is a better performing model than that one? Or does it all wash out, and my as-is system is really no better or worse than my proposed system? So that's what we want to answer with these methods. And so the idea that we're saying here is, well, can we build a confidence interval on the differences between the systems? And so now, rather than building a confidence interval for one system and a confidence interval for a second, let's just say, can we build a single confidence interval for the difference? And if I can build such a confidence interval, then, and this is my generic confidence interval here, just a critical t-value times a standard error, then I can plot that confidence interval on a number line, and if it's totally negative, then I make the conclusion that my mean performance, whatever performance is, maybe lower is better, maybe lower is worse, but they're different, and the mean performance in Model 1 is significantly different than the mean performance in Model 2. If I instead did this, and my confidence interval shows up on the right, then over here I make the other inference. I say, well, now my mean performance in Model 1 is greater than my mean performance in Model 2. But then if I actually include 0, this is like that table that I showed with those regression coefficients. If I include 0, then I have no idea how these 2 compare. I can't make any conclusion. All I know is that at least with this level of sensitivity, then there's probably not that much of a difference between the populations. It kind of depends on statistical power at that point, but this is effectively sort of saying that the systems are probably very similar in performance. And so the question is, how do I build this confidence interval? And so I'm going to show you these three approaches, one that you've seen before and two that we haven't. And effectively, I'm telling you how to build three different types of t-tests. But a t-test is equivalent to a confidence interval. So I'm describing confidence intervals and how to build them. But behind the scenes, I'm actually telling you the mathematics behind these t-tests. But we don't have to think of them as t-tests anymore. We can just think of them as how to build intervals that allow us to make these inferences. So the first one here is this for these paired designs, which you saw in homework 3. And so this is a very special case. And basically, the difference between these three is I'm going to have most of my statistical power here. So when I can, I like to do this one. But I need to specially design the system to allow myself to do this one. And then down here, if I can't do this one, then the next best step is to do this one, which I don't have to specially design, but I need to make some assumptions about the system. But then if I can make absolutely no assumptions about my two different systems, except for them being normally distributed performance data, then I have to go with this one. And so I would like to go with this one because it has most statistical power, but if worse comes to worse, I can go with this one. It doesn't have as much statistical power, and my confidence intervals might be a lot larger, but it at least, there's fewer assumptions. So the more assumptions, the more power. So the first one, again, you've already seen something like this, is when I use a special, what we call blocked design in statistics. And so I create experimental blocks. And this is saying beforehand, I say that I've got my two systems, and I'm going to run the same input into each system. So I'm going to go back to just this picture again. And I would say that I'm going to make sure I have the same number of replications in both models. And I'm going to run the same data into replication 1 for both models, the same data into replication 2 for both models, and so on, so that my outputs are paired. They form blocks. If I don't do that, then it doesn't really matter the relative order of these. I'm just comparing a group to a group. But here I'm saying, no, these two replications are related because they saw the same colors. And these two replications are related because they saw the same colors. I created blocks. And so in my paired difference t-test here that I'm building up to, then the idea is maybe I use the same random number generator for each replication for both models, model 1 and model 2. Or I use the same data from the real world system, which might be my as-is system, to my hypothesized system. And so I run the same things into each replication, but different things into the different replications. So I have independence down the replications, but not within the replications. And why would I do this? Well, if I go back to 380, or I just think about probability, the variance in the difference of two random variables is, in general, the variance of one random variable plus the variance of the other random variable minus 2 times the covariance, how much the two of them relate to each other, the correlation between these two, which I've written out here. So this is the standard deviation of the one variable, standard deviation of the two, the correlation coefficient. And so this here is an expression for the variance of my two mean estimators, the differences there. And so we look at this cross term, which if we assume that they're independent, which we do in the other t-tests, then this all falls away. And the variance of the difference is just the variance of one plus the variance of the other. But if I don't assume they're independent, then I get this little term here, which tells me if I can create positive correlation between the two systems, I have a possibility of reducing the variance in their output. So the idea here is I'm kind of trying to create a fairer pairing. If I give a difficult set of colors to one call center, I want to give that same difficult set of colors to another call center and compare their performance from one difficult set to the other. If I give an easy set of colors to the next replication, I want to give that same easy set of colors to the other system. So it's an apples to apples comparison. It's a fairer comparison. If I do that, then I can create differences within each block. So each block, you get these two replications that have the same set of colors, and I create a single difference. Now the differences will be independent from each other, and hopefully normally distributed, and so in that case I can use a one-sample t-test. So I've now restored independence to my system by taking this block aggregate here and then compare across blocks. And by doing that, I create a mean difference and a variance in the differences, and then I just use a one-sample t-test. And so in a one-sample t-test, the standard error of the mean has this formula. In a one-sample t-test, I have r minus 1 degrees of freedom, and so that tells me how I form my confidence interval. It's just the average difference plus or minus the critical t-value times this standard error of the mean. And so that's how I build the confidence interval for the paired case. And that's exactly what you did in homework G3. And this will be something that we talk more about in the next lecture as we introduce variance reduction techniques. So this is a way of using design of experiments to reduce the variance in your response variables so you don't have to increase the number of replications. Are there questions about that? Our first confidence interval. Our first, you can only use this if you've specially designed the experiment. Okay, so then now the newer stuff. So, well, what if I can't assume? What if I've just been given a data set for one model and given a data set for the other model, and I can't assume anything about common inputs? Well, in those cases, then I assume independence, so now I need to be able to calculate a confidence interval, and I need to be able to sort of see how things change here. So in this case, let's say I make an assumption that although these are independent data sets for model 1 and model 2, I'm going to make the assumption, and I can test this assumption with like an F-test or Levine's test, that they have the same variances, that the data coming out of model 1 has the same spread as the data coming out of model 2. If they have the same variances, then I can actually pool all that data together, not for the purposes of calculating a mean, but for the purposes of calculating a variance. And I would get a better estimate of the variance, which will make for a better confidence interval. And so the variance in one sample I calculate from here. The variance in all of those together is this special formula here. And if you can actually sort of unpack this formula if you kind of look closely. It basically is saying that, well, if I only had these many degrees of freedom from one sample and these many degrees of freedom from the other sample, then this is a way of kind of adding the two variances together, weighted by their degrees of freedom. And so this is my total variance from both samples, which I can only make this assumption if I think the underlying populations have the same variance. And so the degrees of freedom are easy to calculate. It's just the degrees of freedom of one plus the degrees of freedom of the other. So since I had two estimated means, then I lose 2 degrees of freedom. So it's my total number of samples minus 2. The increase in degrees of freedom is going to have a good impact on my confidence interval. And then this variance equation, I can use that to calculate a standard error of the mean. And so all I'm doing is going to take the square root of this ugly thing and multiply it by this square root here, which is like in the one sample case, it's just 1 over r under the square root. In this case, it's 1 over r1 plus 1 over r2. And now I have a different expression for the standard error of the mean. But I can then generate the confidence interval the same way, where I know my mean differences. I just the mean of one minus the mean of the other. And then I know my degrees of freedom, so I can look at the t-value. And I know my standard error, so I can plug into the formula, and I can get a confidence interval. And the last case is when I can't assume they have equal variances. So my F-test fails. And so in that case, I need a new formula for standard error and degrees of freedom. And this is almost the simplest formula for standard error, is it basically just adds the variances together. So that's the standard error of this mean is just the variance of one plus the variance of the other, square root because it's a standard deviation. And so this is our standard error of the mean. That's actually the easiest formula of these. But the downside is the degrees of freedom are really kind of ugly to calculate. So I'm not going through the derivation here, but again, you can kind of unpack this if you squint at it and think hard enough, that this is sort of a way in which I'm accounting for degrees of freedom under the idea that there's going to be more variance from one group and that group may have more or less samples. And so how do I kind of deal with the fact that some of my samples have a high variance, some have a low variance, and this estimate for degrees of freedom takes care of that. But if you have these two formulas, it doesn't really matter where they come from. You plug them into your confidence interval formula, and you now have a confidence interval that you can use on pretty much any normally distributed systems. And so for all of these, I can plug them in to this formula here and use this interpretation. So those are three different types of t-test, three different types of confidence intervals. But in the end, I'm just wondering, is 0 in the confidence interval? So that's kind of the rule that you figure out what world are you living in? Are you living in a world where the two models are paired? Are you living in a world where they're independent but of equal variance? Or are you living in a world where they're independent but of unequal variance? From there, you choose your degrees of freedom and standard error. And then you calculate a confidence interval and you forget about the context. You plot your confidence interval and you ask, is 0 inside the confidence interval? If 0 is on the left side, then I conclude that one system is significantly larger than the other. If it's on the right side, I conclude the opposite thing. If 0 is in the middle, I can't really detect any difference. But if I have tight confidence intervals, it might be safe for me to say that the two systems are practically equivalent. So any questions there about our two-sample case? It's just a graphical way to unpack three types of t-tests that you use in three different situations. Many times in ARENA, you'll default to paired t-tests because you'll get the same random numbers going into the same, every time you run ARENA, even when you build a new model, if you reopen that model, it will then run with the same random numbers. Now, if we want to make sure that they're absolutely dependent, like that they're blocked pairs, then we use this common random numbers thing that we'll talk about in lecture K1. But if you have two systems where the only thing differs is the value of a parameter, so you're pretty sure that the sequencing is going to be roughly the same in those two systems, it's probably safest to actually use the paired t-test and not the independent t-tests. Because you don't want to use an independent t-test if they're paired. It totally violates the assumptions. All right. So newer stuff so that's fine if I have two systems, but in most cases, you're going to have multiple systems. And so the question is, how do I rank and select from multiple systems? So here's the new system. So I say, well, I told my boss that I'm about to run this simulation study, and the boss says, wait, you think you can bring the utilization down so that our operators are only 50% utilized? And say, yeah, it's kind of what I was thinking. And then your boss, being the selfish bastard that he is, says, well, what if we can fire one of them? You know, so now the utilization it was 50%, but he says, you know, I'm actually happy with 70% utilization. So if you can get them all down to 50, then we don't need one of them, so we'll get rid of them. So I want you to throw in this, and you say, oh, but the ethics of it, and you say, you know what? I don't pay you for your ethics, and so then you then put in these three things here, and then now you have to compare these things honestly. So I've now got the problem. I've got three means, and I don't quite know how to say which one's better because there's variance in all three of these performance estimates. So it's not clear that I can say is one better than two, and how does one compare to three, and what if I get this funny thing where I say one's better than two, and two's better than three, but three now for some reason looks better than one. Like, how do I deal with the fact that there's variance in these performance estimates? And so the straightforward approach, which is the approach most people kind of think of doing initially, is to just do all pairwise comparisons with a two-sample t-test. So I could go through here and I do a two-sample t-test, a confidence interval between these two, between these two, between these two, and I guess, is that all? 3 choose 2, 3 times 2. I feel like there should be more than that. But I think that's right. So I just do all of my comparisons with that. Now this gets to a much, much larger number. If there's like 6 of them there, then the combinatorics go much, much higher. You know, that's 6 choose 2. So that's 6 times 5 times 4 times 3 times 2 times 1 divided by 2. And so you end up getting a lot of comparisons. But you could just compare them all to each other and then ask, what does the t-test say with respect to the statistically significant difference between all of these? And so this is the standard way you think of these things, and there's going to be k times k minus 1 over 2 comparisons here. And every comparison is just going to be a two-sample t-test. You calculate a pairwise confidence interval, compare it to 0, and then based on whether 0 falls in that thing or not, or what side of it falls on, then you rank within that pair one greater than the other. And then from those, you can hopefully then get a rough ranking of those different model systems together. The problem with that is that every one of those confidence intervals has a false positive rate. And so it's possible that all of your systems are equivalent, but you're going to get a couple of detections. You are going to detect a difference of one system than another, and you will just come up with a fictitious ordering. And so this is what we call a family-wise, and I've already talked about this a couple of times. There is a family-wise error rate on this ranking problem, and it comes from the independent error rates, the independent false positive rates, on each of these confidence intervals. And so if there's a 5% chance you're going to accidentally rank one thing over another, then there might be a 90% chance you're going to detect an ordering when it doesn't exist. So it's only possible to keep your family-wise false positive rate low if your individual false positive rates are really, really, really low, which is going to mean your confidence intervals on these individual comparisons are going to be really, really, really large, which means you're probably always going to have 0 inside them, which means you're never going to detect an ordering. So this seems to be a problem. And so this is, what I've sort of just summarized here is this Bonferroni approach to this problem. If you just set each individual false positive rate at 5%, the family-wise false positive rate is going to be much, much, much larger. And so it could be 100%. It could be that you are guaranteed to detect an ordering when an ordering doesn't exist. So the straightforward solution is just to divide each individual false positive rate by the number of comparisons. So back here, I have k times k minus 1 over 2 comparisons. So I would say I want a family-wise false positive rate of 5%. So I'm going to do 5% divided by that giant number of comparisons, and that will bring my individual false positive rate down to a very, very small amount, which is going to make my individual confidence intervals gigantic. And I am pretty much never going to be able to detect a difference between them. So that'll be the problem. But we can do that. And if you go into the output analyzer and you open up the one-way ANOVA and you put in all of your systems, call center 1, 2, and 3, under comparison method, you can select Bonferroni, and this is what it will do. And so for a small number of comparisons, this is a fine way to go. But as you get to a larger and larger number of comparisons, then you start thinking about this ROC curve. As your alpha, your type 1 error rate goes lower, your statistical power also gets lower. So as your individual false positive rate goes to 0, your individual ability to see any true positives also goes to 0. So you lose all your statistical power with this Bonferroni correction. And so that's why in classes like 380 and 385, we introduce the ANOVA. So, and then what sometimes we don't introduce, but what you'll end up seeing in the real world is once your ANOVA detects a significant difference, it just tells you there is a difference between these three models. You run what's called a post hoc test. And in one shot, without doing all these pairwise comparisons, it can rank and sort them. So what I've got here is I've got these 1, 2, 3, 4, 5 different groups that all were measured along this one response variable here. And they all have these box and whisker plots. So you can kind of see that there's like a pattern here. The ANOVA comes out significant. It says there is a difference across your treatment levels, your factor levels here. So one factor ANOVA, so it's got this 1 here, and it's got these 5 levels. And then the post hoc test puts these little letters above it. And what those letters mean is it's grouping them statistically together. These two that both have an A, it says they might look like they're different, but it turns out that I can't tell, that really just might be random chance that this one was slightly higher than this one. So I'm going to put them in group A. Over here, I can say these I'm putting in group B together. I can't tell the difference between the two of them, but they are definitely higher than this group over here. So they're in B because they're definitely different than this group. And then this intermediate one, it says I can't actually tell the difference between this one and either of these. So I'm going to put in a special intermediate group called AB. And so when you do your post-hoc tests, it effectively gives you all these labels, which allows you to do ranking and sorting. And so actually in ARENA, and I've mentioned it down here, you do have the option under comparison method to select 2-key. There's another one as well that there's, again, statistical power implications for which one you choose, but then it will effectively do this for you. So it looks like that solves all our problems. We run 3 models, we do an ANOVA, we do a post-hoc test, and it ranks all of our models. And we can say, aha, this model is better performing than all the rest, or at least I don't really know the difference, but one of these two is definitely a good one and all these are bad. So that could be the case, but it turns out that this approach is not ideal for simulation studies. For one, because in sims, we like to be able to run a pilot study and then use that pilot study to then figure out how many more replications we need to run. Question?
Yeah, for the Bonferroni correction, what would be the difference between alpha over K and alpha over C?
Well, so the C that I used here, I might have in previous slides used a K here. I was just trying to make it clear that I'd use K for a number of systems, and then so this is my value of C, this number here. And so I just didn't want to use lowercase k here to cause confusion. So this lowercase c is the number of comparisons, which in this case, if I have k systems, this is the number of comparisons, that's C. And if I were to try to do this with Bonferroni, these might all be grouped in the same group. So we don't necessarily want to run 1,000 replications of every sim if we can get away with 5. So we've already seen these ideas where you run a pilot study and you see if you need to want to run more replications. We would like comparison approaches that allow us to do that thing where we trickle on more replications only as needed. And we also often don't care about the whole ranking. We oftentimes just really want to care about just who's the best. I just need 2 groups, the best and everybody else. And so, so maybe we can engineer other comparison methods that have fewer comparisons that allow us to capitalize on sequential sampling and only pick the best. So as an example of that, one of those could be, well, let's just rather than trying to rank everybody, I'm just going to compare everybody to a benchmark. And that benchmark might be the as-is system, for example. And I'm just going to do the same straightforward method of all my pairwise comparisons. But now that I'm not comparing everybody to each other, I'm only comparing them to the benchmark. And I'm really just asking, are there any differences from the benchmark? So do these factor levels matter relative to a benchmark, not necessarily relative to each other? Then now I only have k-1 comparisons. So I have far fewer comparisons. So if I only have 3 systems, I'm only making 2 comparisons because I'm just comparing each system with the benchmark. So now I might be able to use Bonferroni correction and not wash out all my statistical power. So that's one example if I can redesign my test to have fewer comparisons. Now that's still not quite ideal. Like what if I really want the best system? Well, there are procedures like this one outlined in your textbook for selecting the best that allow it to do it with as few samples as possible. And they don't rank everybody, but they at least then output just who's in the top group with some precision. And so I set this thing up by saying I've got k models, I've got a confidence level, which I'll define down here. I define a practical significance. This is kind of like my effect size. I say that I don't care about systems that differ by less than this amount. And then I say I want to run no more than 10 replications on my pilot study. And then I'm willing to look into run a few more replications to discriminate. But at least initially, I only have enough computational budget for these 10. And so the way this test is defined, our confidence level is such that if our selected model was not best, the probability that it is greater than epsilon from the actual best is going to be equal to alpha. So in other words, if our selected model is not best, there's going to be a 95% chance it's really close to the one that actually is the best. That's the way this test is defined. And so the way it runs, and I won't go through all the steps here, is they basically, and you can read more about this in the book, they run a little pilot study with their 10 replications of each. They do a ranking step, which basically does a Bonferroni corrected pairwise comparison of all of those. And then that generates two groups, a group that is clearly better than the others. And then within that, the group that is better than the others, you run an additional number of replications, and they put a special formula for exactly how many more replications you run. And then from there, you just compare the means within that subset, and you pick the one with the best mean. And so that requires very few replications, and you still have this nice interpretation back here that you are pretty confident that you're going to pick a system that is pretty good. It may not be the best, but is not far from being the best. So that's an example of smartly defining your test. Now you might say, I don't want to go through all the algorithms for this. Well, fortunately, somebody else has done the work for you. So if you go into the process analyzer, you give it a bunch of scenarios you want to compare. You go into charts and say, I want a box and whiskers charts. One of the options is to select the best. And behind the scenes, the process analyzer will do an algorithm very similar to the one that I just gave you, and it will put in red the ones that it says are in the group that's the best. It's saying, I don't know which ones are the best inside this group that's red, but if you pick either one of them, they're not going to be that far from each other, and they're both going to be much better than all the other scenarios you gave me. So you don't even have to implement these algorithms for you, they're already built into the software. So then the last example of this is gets even more sophisticated, where you say, I don't want to even figure out what scenarios to run. I just want to give you one model, and I don't know, so I don't have multiple models. Like here, I could have 3 very different models that aren't just like parameterized differences from each other. But if I have one model, and my different groups are just different sets of parameters, then I can go into these simulation optimization software packages like OptQuest inside Arena, and I can say, here's my one model, here are all of my decision variables and all the things that I want you to step through, and here are constraints. Like I need to make sure this response variable never gets higher than this amount or lower than this amount. Like this could be temperature in a reactor. I want you to optimize the reactor performance, but you better make sure that even though the response variable, like energy use or energy production is maximized, I do not want to maximize energy production if it means I'm at critical temperatures in the reactor. So I want to optimize my energy production subject to my temperature staying in safe ranges. And then you can watch as OptQuest does all the work for you. It will, in time, go through simulations, running as many replications as it thinks is necessary. The red line here are things that violated your constraint. The green line are things that are feasible, that stayed within your constraint. And the level here is the thing that you're optimizing. And so I can watch it step through these and says, oh, it went too high and it's infeasible. It restarts at a different level that's feasible and then allows things to minimize. And so it does all that for you. And OptQuest isn't even something that's arena specific. The OptQuest engine, which has a proprietary meta-heuristics behind the scene, is licensed to many other sim packages. If you take 477 and you use any logic, it's in there as well, the exact same tool. So those are basically the different ways that we can do ranking and selection in ways that are more efficient than doing it all manually by hand with pairwise comparisons. Any questions? All right, so my attendance question for you is that I said that you can use these so-called post-hoc tests to rank a bunch of different options. But I said that you can only run a post-hoc test after another test says that there is a difference, there is a significance. What is the first test you have to run before you can run the post-hoc test? So this is the test that you've learned about in like 380 or maybe 385. It's like a grown-up version of the t-test. So you can't run a post-hoc unless this thing is significant first. Otherwise, that's all I've got for you today. Remember that survey is online, 4 points bonus on homework credit. It disappears Monday night.